I was asked to do the role of structure, and it made me go back to memory lane about the role of structure. So I'm going to go in a number of different topics. So what?
Maybe you need to click the slide or something. I don't know.
Oh,
Those you lose focus.
recording the thing. I have to okay. Okay, so I'll go back. So we're going to discuss three topics. These are the study of collective flow and high density equation state, the nuclear liquid gas phase transition, and the isospin dependence of the equation state. Okay, so we're talking about the role of structure on equation of state studies, and it's a fact that almost all nuclear equation of state studies use projectiles and targets. They're spherical, and you could ask why, and I have a whole slide explaining why. Basically, it's because of cost. Deformed targets more expensive. Okay. Also, you don't need deformed targets, but we measured flow with the deformed Samarium 154 target, which is very deformed. Why? And that is to convincingly solve a puzzle encountered in collective flow measurements a number of years ago. So first, I'm not going to assume everybody knows expert on flow. So there are three kinds of flow, you could say. Of course, there are many different Fourier components. So I'm just going to talk about radial flow. They have a very central collision, then the matter expands outwards after compression. Okay, and expansion gets bigger with higher energies. And then there are two flows illustrated in this figure here. So where's my pointer? Okay, so here is a projection. Here's the five different stages of a heavy ion collision of 1 GeV, gold and gold. Here, each separated in time. The time is indicated here. This is a slice through the system measuring pressure contours. And here are density contours. And what you see is a function of time. The matter starts to squeeze out top and bottom. That's squeeze out, sometimes called V2, or nowadays called V2. And this energy is very strong. And then at this energy, there is also a second flow component, which you can see in the vectors of the momentum here in this plane going off to the side. And in this figure here, the convention for V1 is that this is, if you're deflected to this side, the angle is measured with respect to this side. Cosine of that angle is 1. So this would be a positive V1. And then over here, you see the squeeze out, that's at an angle of 90 degrees, cosine of 90 degrees, 2 times 90 degrees is pi, so it's negative. So the convention is that V1 is positive, V2 is negative. And of course, this data has been used to extract the equation of state. That was discussed earlier, and many times actually during this talk, this meeting. Okay, so now the question is this always the correct sign for V1 and V2? And there's reasons to believe that it might not be, because actually at low energies, and there's an attraction of low densities, and like in the case of the optical potential, these two nuclei feel an attractive force, and they could just go around. And so instead of what the conventional flow is that you bounce off, you could actually go through to the other side. Of course, we have the conventional approach in flow that there's matter bounces off. And so if you measure particles out here coming up with large transverse momentum, you don't really know, unless you have some physical reason, that it's orbiting or bouncing off. Okay, seems academic, but actually a number of years ago, Gary Westphal was doing experiments with a form pi detector and measuring flow. And he found his reaction plane, and then he went to calculate the transverse flow, and here was his flow. This is argon plus scandium. It starts off big, goes down to zero, and goes back up again. Okay, well, that's a little strange. And of course, he remembered that nuclei attract the optical potential, so he just inverted it. Okay, so he just took everything here and flipped the sign. And then he varied the energy and found where it went to zero, and that was his disappearance of flow meter. But so this whole problem relies on the fact that conventional flow analyses with the looking at leading particles in forward and backward directions can't distinguish between negative transverse momentum or which are attractive from attractive force or repulsive momentum transfers. This thing just assumed that it was attractive at low energies, but why not prove it? Okay, so we're experimental, so we tried to prove it. The way we try to prove it is to choose a deformed nucleus, choose a low enough energy that we don't destroy the deformed nucleus after collision. The deformed nucleus rotates, and then so let's say we have here. Where's my so. A particle comes in, it hits the target, let's say it's on this side of the target, it is bent over to this detector. The angular momentum is up. The circular polarized photons coming up are up. I put a circular polarimeter up, and I see whether it's polarized up or polarized down. If it goes on the other side, here, then it can go into the same detector here, but it bounces off. The nuclear spins in the opposite direction. The polarization is down. It's a little bit more complicated than this because the analyzing power of the polarimeter is only 2%. So you have a lot of symmetries. You have detectors up and detectors down, polarimeters here, polarimeters there. But if you take a look at the result, you see that the polarization at low energies for both peripheral and which are in the open points and mid-peripheral collisions are positive. Those polarizations mean it's attractive, it's orbiting. But then as you go up in energy, starting at 35 and going up to 150, the mid-central ones go to the other side. So we're seeing things bouncing off in the conventional technique. So this is an example of nuclear structure coming to the rescue. Okay, now flow, of course, has quite a long history now, and flow is quite nicely measured. And I took something from the white paper for nuclear transport theory. These are data from HOTAS comparing neutron and proton flow values, and they're quite nicely measured. But at lower energies, you don't just have neutrons and protons, you also have clusters. And here is an example of the transverse flow, the V1. Of course, it's dpy, dx, dy. It's a little bit different variable, but basically V1. As you go up in mass, the flow increases. It's really large for the heavier fragments. At higher energies, you don't have these heavier fragments, but you have, when you have clusters, you have to correct for the flow of the clusters. But most transport theories don't do that. Okay, so why?
Why the increase is not linear?
What?
Why is not linear?
Well, the reason why it's small is because there's a lot of random thermal motion. And then as you go to the heavier masses, thermal motion basically does it.
There's no coalescence picture.
This is theta. I'm not showing calculation.
I know, but in biology, we clearly say, okay, they just add up, right? The flow add up with the mass number.
Where coalescence works, yes,
Yeah.
but I don't think you coalesce some of these heavy fragments. You could go up to the same mass 3 or so. Okay, so complication, cluster production influences the calculation of nuclear emission above about 400 MeV, and most nuclear transport models don't describe the binding energy of clusters with A greater than less than or equal to A greater than or equal to 4. It's not a very large problem at high energies, because there are not many heavy clusters. And what you can do is if you don't want to do any clustering, you can either make a simple cluster model like they do with the QMD calculations, minimum spanning tree, for example, or you could just break them down into effective nuclear flow and just calculate the flow that way. Because the momentum are really not changed that much by the clustering. But to go to beyond this approximation, you can try to increase the number of species in the transport code and really dynamically calculate deuterons and things in the matter. But the problem with that is that you don't carry these particles all the way through the calculation. In high densities, inside of something like a third of saturation density, those clusters dissolve. That's called the that's a proper. They basically they dissolve. Basically, you don't get any kind of. You can try to make them, but they're basically blocked. But it put less than rho equals rho naught over 2, you can produce it by nucleation or spinodal decomposition. And that has to be in your transport code. Okay, now here's an example of the state-of-the-art transport code. And so this is a calculation by Akira Ono. The paper is by Kaneko-san. And what is shown here is the ratio of the deuteron spectra of the proton spectra. And there are two calculations here with different equations of state. The red one is given by this line here, the symmetry energy of this line. And they both have the same symmetric kind of equation of state. So this is the red line here. That's this orange curve here, and that's closer to the data than the green one here, which follows this green line here. Okay, not only for the DP ratio, but also the TP ratio and even in double ratio. So clearly, this curve is better than that curve for the symmetry energy, and it actually is consistent with the low energy density constraints that we already got from other with nuclear structure and also low energy reactions.
What's the difference between those two models?
The L values. So the good one is 55 and the bad one's 162 or something.
152.
162.
152.
152. Oh yeah, it says right there, 152. So I don't have to remember it. It's actually on this side. So that's a pretty stiff question. And what I want to get the calculation to be changed so that it's stiff here, but it goes over to the one we already know from experiment. And I'll try to convince the Kira to do that. We'll see if we can. So do the constraints agree with theory? Okay, so I showed you the low density constraints here. Those are the ones I was complaining at. Here's Carl effective field theory in blue. We know that there's some difference in high density. Maybe it's Carl effective field theory. It needs to be more stiff. The data have large error bars. If you ask what happens when you put all these constraints here and combine neutron stars and everything that you have, then you get a constraint basically goes like that. So it's a little bit softer than what you would infer from these data points here. Okay, but high densities are the main difference here. Okay, so now I want to change to another subject, which has to do with the decay, with multifragmentation, and some people like to say the liquid gas phase transition. So this is an experiment which could be done at Brookhaven, because fragmentation occurs for every system if you have enough energy. So if you make a hot nucleus and you put a GeV or so of energy into it, it will expand. And as it expands, it will decay. And the decay rate really exponentiates as this thing gets down where the binding energy gets low enough that it's actually better bound to have the matter condense into droplets like alpha particles. And that's what's happening down here. Okay, and so it basically the physics is all given by statistical physics and a little equation of state physics. And this is my point here. In this group here, this particular case, there are 3 different cases where you can see fragmentation. One is in central heavy ion collisions, and you raise the energy looking at central collisions. Or you can go to large impact perimeter heavy ion collisions. And this is a plot of the number of fragments with z greater than or equal to 3 as a function of the total charge that's bound of all fragments. And you see that there are more than one set of data. These data differ by bombarding energy, 400, 600, 800, 1000. The curves are all the same. This is well known. This is called limiting fragmentation. This is well known. And it will still be the same thing in Brookhaven, except it'll be at larger effect. Okay. So the other one is light ion induced.
So what's the y-axis again? So this is,
Y-axis,
yeah.
this is the number of intermediate mass fragments. An intermediate mass fragment is defined as Z greater than or equal to 3. It could include the really heavy ones, but they're not really heavy. So usually we don't count the heavy ones in the intermediate mass fragments. Okay, so now the way you can describe this thing in certain cases is by assuming that you have nuclear statistical equilibrium. That's a general theory. It's used to do stellar burning processes. It's well defined. There's a theory, if you remember Hauser-Feshbach theory, you probably only encountered it in terms of compound nucleus. But if you go back and read the original paper, he also took full reaction theory of all the scattering. The only thing you're doing is throwing at all the phases. Okay, and you can calculate reactions, everything with Hauser-Feshbach. All you need to know are optical models and level densities. Okay, so if you want to calculate the decays in this pure statistical thing, you need to know the thermal excitation energy, the charge, and the mass. Okay, and you may need to take some account for a collective motion. Maybe it's expanding. And this is a particular set of data compared to an equilibrium model. These are data where gold at 35 per nucleon. These are the multiplicities of fragments in a central collision. And these are different calculations depending on different excitations at energy per nucleon or temperatures. You see, the statistical physics is very good. Okay, it's better than most other reaction theories in terms of absolute errors. That may be a little bit of an overstatement. It's certainly better than the optical one. Okay. So this thing, what is the content of this theory? Well, you have to have this thing is an equilibrium theory. It has abundances that are produced, and what do they depend on? Some geometrical factors, the chemical potentials for neutrons and protons, or baryon numbers, and there's something having to do with charge, so that would be. So you can parameterize it. I would prefer to do neutron number, proton number, and then there's the internal level density or free energy of the fragment, combined in a fragment. So if you can know this function here for every single fragment, it's equivalent to knowing the equation state. That's just a fact. If you perform several experiments with different A and Z, you can define the chemical potential, and the internal free energy of your nucleus is this quantity, which is the main unknown at very high excitation. You may even need to know the temperature and the volume, or equivalently the density. Now, the free energies are known at low excitation energy. You can just look them up. This is a compilation of all the levels, low-lying levels in carbon-13. It's a lot of work to put that into your code. Probably several months. We did it. And then you have to couple that to the high energy temperature dependence, and that's where the new physics comes. Okay, but you put this in. Now, why do you care? Because this is a small amount of the total base space. You care because every single decay goes through these little line levels. What you measure depends on what it decayed from. So putting this in the code is tedious, but it's absolutely essential. And if you do this here's an example, and this is not an unusual example. You start off with the primary hot fragments. These are the fragments with the very high excited states. They look something like this dashed line, but after the decay, they look like the red line, and the black points are the data. And then all these ups and downs have to do with the level densities and the levels that you pass through to get down to the bottom. Okay, what questions are there? Okay. Now you can do other things. I mean, one question, of course, relevant to thermal physics is what is the temperature? So that's so there are several ways you can measure the temperature. One is that you could take two levels in the same nucleus, lithium-5 is very nice because the level is very high in energy. You can take a simple experimental definition of the population. Take 2J plus 1 or 2J2 plus 1 times the difference in the excitation energies over temperature. This is basically the ratio of the two terms in the partition function. Now, of course, because of the feeding will change this number. This is just a number, okay, that you can use to extract temperature. You can calculate it theoretically and measure it experimentally. The other thing you can do is calculate the isotope ratio temperatures by taking two isotopes. They also depend on temperature, and it works out like this if you choose the right combinations of isotopes. And this is just a consequence of your chemistry theory of the law of mass action. That's on your chemistry textbook.
At the same temperature.
Yeah.
You have the same P energy.
These things are all coming from the same experiment.
So then you assume the same temperature, the same P energy.
We choose a temperature for this beam energy. A different beam energy will have a different temperature. Okay, so this is what it looks
I
like.
think his point was just that that's why when I do all the different isotopes are from the same experiment.
Yes, absolutely. You have to measure them all the same. I'm sorry.
No.
Okay, so this is if you just do the naive calculation of temperature by the formula I gave you in the previous page, and you do things like these ratio of two states in lithium-5, helium-4. There's a state in helium-4 20 MeV. Boron 10, you get numbers which are sort of similar. And then here are the calculations in blue. The calculations, I think the data are in blue and the calculations are in red, but I'm not quite sure. Anyway, the data are treated, the calculations are calculated, you get the actual yields, but then you plug it into this formula to get the apparent temperature. Okay, and you can see that they're quite in agreement that the actual temperature of the system that produces is 4.2 plus or minus 0.6 MeV. And if you go over here, for the isotopes, you get about the same number. Okay, but you can see there are big modifications coming. Modifications are coming from all this feeding process that you have to take into account. And I know you guys do this at high energy, so this should not be surprising.
So you have to correct the apparent temperature to a real temperature by taking out.
Well, the real temperature is what I put in my calculation. That's what I quote right here.
Yes, okay.
Okay. Okay. The apparent temperature is what you get. That's what the foreman does before he has a real temperature. Just by taking the numbers.
Sorry. So the jump is because of you said the
Real correction.
What you're asking why some of these are bigger and some of these are smaller? The reason why some are bigger and some are smaller is because of the second sequential decay. Some of them have bigger sequential decay effects, more feeding. The lower temperatures are coming from isotopes, which sort of get a lot of decays feeding into it. So you really see the ratios of the ground and the excited state, what you would get from combining all the things, including the low temperature emissions. The other ones are cases where you're only fed if you're very high. Yes.
Horizontal axis is
These are this is the binding energy difference given by this quantity here. Right?
of different combinations.
Different combinations. You have to have nuclei with different binding energy. Okay, or different levels. Okay, so the main thing that's going into this is precision structure, and of course some experimental data. Okay, you can even use this to determine spins. So this was a spin in boron 8. This black line was not tabulated, but we could just go through and compare it to our statistical calculations. From that, we learned it was what everybody thought it would be, 1+. Okay, but people are using these kind of techniques now all the time to try to determine amount of states. Okay. Okay, so the last thing you can do here is you can test chemical equilibrium by constructing chemical potentials. So you take You have, here are different isotope distributions. So these are 4 systems here. Tin 124 plus tin 124. The blue one at the bottom is tin 112 plus tin 112. Of course, tin 124 has 4 neutrons. And then we have one case with tin 124 scattering off tin 112 and tin 112 scattering off tin 124. We look at different rapidity regimes. And those 2 cases which involve the same reaction partners, tin 112 and tin 124, in different rapidity regimes give different isotope distributions. Okay, now it looks really complicated. But what we find is if we take the isotope distributions for one reaction and divide it by the isotope distributions for another reaction, if they're presumably at the same temperature, which we can arrange, then these ratios just make straight lines and blah, blah. And that's basically given by the number of neutrons times the difference in neutron chemical potentials of the 2 reactions over temperature, the number of protons, the difference in proton chemical potentials at the same temperature. So you can test the degree to which 2 systems, in this case, these 2 systems, tin 124 plus tin 112, which were colliding, were in equilibrium at the time that they separated apart. Okay. So you've been very patient and asked very good questions, and I'm done. Thank you.
Very nice. Any questions, more questions?
If we go back to this slide, what's the beam energy for this,
Which one? Oh,
the acetone?
I can go back. Okay.
Filling plot.
This one?
Yeah.
This is a reaction that was done at 50 MeV per nucleon here. I mean, 50 MeV per nucleon is a nice, where's my, 50 MeV per nucleon is a nice energy because it's not going too fast. If you did it at 30 MeV per nucleon, they would come to equilibrium very nearly so. If you go to 100 MeV per nucleon, then they will be less.
So what will happen this scaling for other high or low energies?
The scaling appears to work.
Always.
I think it gets maybe worse at higher energies. We're still trying to figure out how much worse, but we have data that we took recently, and 150 MeV per nucleon, the scaling is quite good there. But we have some data that we took at 270 MeV per nucleon Riken, and in some rapidity regimes, the scaling is not so good. And we're trying to discuss why that is. But for the central rapidity domain, the scaling still works. But if you go to forward or backward rapidities, it doesn't work.
Yeah, Fuchang, go ahead.
Bill, this is Fuchang Wang. I have a question about your so D over P ratio, triton over P ratio sensitive to the symmetry energy slope parameter in the soft.
Oh yeah, so I think let's go back to that one.
Right.
What's
At the beginning
Oh,
of your talk. My question is,
okay. I don't. I just turn it back on again so I can page through it.
yeah, but
So let me see. Which one are you talking about?
yeah, the neutron over proton ratio.
Oh, this is calculated one. This one here.
Yeah, the calculate. Yeah, this one. Yeah,
Yeah. Right.
And
Yeah.
the data, yeah, and that data favors the softer equation of state. You know, the negative thing I understand, of course, but how certain? What is the uncertainty in the calculation? What you know the overall value of the ratio, model uncertainties, model dependencies?
My guess is that they're still large. The calculation's been done many times, and I think in comparison to other calculations, transport calculations regarding the isospin degree of freedom, it's probably the best calculation. But I don't know when you see a discrepancy between data and theory, whether it's because you have the wrong parameters for the equation state or there's something missing in the theory. There really isn't any other comparable models. So you would like to have 2 models which were of the same level of detail. And I would say there really isn't another comparable model that takes into account the clustering. And when you look at the guts of the model, you may find a quibble here or there, but whether that really reflects itself in the predictions, I'm not sure.
Right, but if the red model and the green model, let's put that away, if the values are uncertain, if those all those curves are higher, then you raise all the curves up, then you
Okay,
can.
so looking, let me see. Here it is.
Yeah.
So here's the two red curves. This red curve with that data, this red curve here with that data. This red curve now is significantly below that data. Over here, I think the error bars are pretty big. So I would say here it doesn't work very well. And I'm not really selling this model to you. I'm just reporting on what it does. I don't know why the model sometimes succeeds in some observables more than it does in others. And what I think, since it's really important for us to have good transport models, we work closely with the theorists to try to give them data to compare with their models. But I, of course, spend my time trying to interpret what seems to be missing in the model. And in this particular case, one of the key things I would like you to take away from this talk is that nuclear structure information is important. This clustering is another example of it. These clusters are moving very slowly relative to each other when they capture. That's the essence of the coalescence mechanism. In this calculation, there are forces between these. There are forces between these particles, and they influence whether the particles are captured or not captured. So this is different than having an overall equation of state. This equation of state is built up from forces. And maybe this information gives us some indication that the red force is better than the blue force. Certainly the red force seems better justified to be than the blue force. Okay. But we're in a stage of really trying to weed this out. I don't think we know the answer to all the questions. Yeah.
Thank you. Fair enough. Yeah.
So, I mean, intuitively, it's very easy to understand looking at the excitation level, measure the temperatures, or at very high energies, when measuring the particle abundance, you measure the temperature. The last topic you mentioned about the cluster size related to the temperature chemical potential. Do you have an intuitive explanations? Is it because when you make the cluster size, it's the Fermi potential which create up?
No, we have only two in these in the data. Okay, in the data we only have two chemical potentials, proton and neutron.
Yes.
So the chemical potential of a cluster is just the chemical potential of proton, the number of protons. I mean, Z times the chemical potential of protons plus N times the chemical potential for neutron. So there are only two parameters.
Yes, but why related to the cluster size?
It isn't.
Can you show that?
Yeah, I think
Sure,
if that came out, yeah, so maybe it went too fast. So let's just go back to here. So I blew it up. I blew the
This
point.
one, yeah.
Okay, so on the left-hand side, you're seeing the abundance. Okay, the abundances reflect all sorts of things, not just chemical potentials. They reflect mining energies, they reflect temperature, etc. On the left-hand side, each one of these points here, this is a ratio of the proton yield, the lithium-6 yield in one system over the lithium-6 yield in the second system. It's the lithium-6 yield in the neutron-rich system, tin-124 plus tin-124 divided by the lithium-6 yield in the neutron-deficient system, tin-112 plus tin-112. As we increase neutron number to lithium-7 and lithium-8, we see this number goes up. Okay, that reflects the difference in the change in the chemical potential overall for the neutron and the proton. As you go more up, then the So they did, so that, this ratio reflects the difference in chemical potentials here. So this curve here is going on the changing neutrons. So that basically is given by this exponential times the number of neutrons times the difference in chemical potentials for neutrons in the system divided by temperature.
So,
We assume the temperature of the two reactions are the same. They're pretty close.
assumption is the temperature in the two systems are the same. What change is to create the clusters, you
What's different
only
is
need the density.
the protons, number of protons in the two reactions are the same. The neutron numbers are different. And in this simple picture here, this ratio is given by, so we're going along this line here, so we're only changing neutron number. So we're only changing this first term, n times delta neutron chemical potential over T. Delta neutron chemical potential is the chemical potential in the neutron-rich system minus the chemical potential in the neutron deficient system.
And the cluster, the abundance of the cluster here depends on just the chemical potential and the temperature.
It depends on many things. It depends on the temperature, it depends on, you know, the density and all that. But in this reaction here, we chose two reactions that are so similar. We can assume that the densities in the two systems are about the same. The temperature is about the same. So the main difference here in these two reactions is just the difference in the neutron chemical potential. Of course, the more neutron-rich system has a different chemical potential than the more neutron deficient system. And you can do the same thing and make plots here where you keep the neutron number the same and change the proton number. And those curves in this, those sort of curves go in the opposite direction. Okay, and just for this system, it's an accident, but just this system, the chemical potential of neutrons is minus the chemical potential difference for protons. But that's not true for all systems, just this system. It's this particular tin and tin system. So the differences between the yields in one and the yields in the other are just given by this R21 factor. So if I gave you all the yields for tin 120, 112, and that number, those three numbers, you could calculate all the yields for tin 124. Yeah. So that chemical information is really simple. In a thermal way, it could be more simpler.
So can you go to just example what you showed the symmetry energy versus the density? So I just always wonder in the low energy,
This one.
yeah, this one's fine. So how in the low energy in general, how one estimate the density in the system? You see this data error bar, horizontal error bar, right?
These. So let me give you an explanation here. Okay, this is a theory calculator. Okay,
the data point of horizontal error bar.
this one here. Okay.
How
This
much-
is this was actually coming from the last set of data that I described. So it turns out for that particular set of data, in theory, these two things are very peripheral. And so for a period of time, they're overlapping. And then the charge is going and neutron number going back and forth from the two systems to seek equilibrium. But at this energy, they separate before they equilibrate. So this is a measure of the equilibration rate. So you could do this in a transport theory and ask what you have to do with the symmetry energy of that density to reproduce it. There is a big uncertainty, so there's a big error bar.
But my question is in low energy.
So then you find out, then you go and plot, you plot all of the possible equations of state that give roughly similar results, okay, because of course they give different results. You find that all these functional curves cross at one point. That point it crosses is at about 0.22 times saturation density. And so that's where we plot that density, but there's a big uncertainty because it could be from 0.17 to 0.34. So
But
that's
it's
what they-
no, it's not a measurement, it's using the model to calculate the. density.
Absolutely.
It's like the heavy ion impact calculation from a theory. In principle, it's from a theory, it's not a measurement.
Well, the theory would have nothing to go in it.
Well, actually, I did mention in my talk, anything that's a HIC. That's the heavy ion collision, and we rely, for heavy collision, we rely on transport model. And that's one thing that we said, we really need the transport model to be up much better than current available.
Okay, so
And
now,
that's where our error.
so now let's go to another point here. Okay. These are points here. It's like Betty explained this point here from Alex Brown. And that was also one look at the symmetry energy functionals to describe doubly closed nuclei. They all crossed at about 2/3 saturation density, and they had a value of 24.7 plus or minus 0.8 ABD for symmetry energy. This one over here, this one comes from analysis of isobaric analog states, and that was, I put this plot from the narrowest point in his contour. Okay, but Pavel actually did a Bayesian Pearson correlation analysis of all that data and obtained a symmetry energy functional from this density 0.2 up to about a little bit over 1 times saturation density. And if I could show you, I was put in my talk, but I thought it'd be too much. I can show you the overlap of that symmetry energy functional and this. They are completely independent sets of data. Ours goes right down the middle of his. Okay, they're within error bars. So I don't, and then there are other things. I mean, you have chiral effective field theory. I mean, this stuff, there are some uncertainties, but there really aren't that many large uncertainties in subsaturation density.
But
It's different at high density.
I think it's just as a general question, in the low energy reaction, but also in the low energy heavy ion collision all the way to, let's say, NTeV, where you get the maximum density. So the question is, first of all, like how do you put that density? If you do the measurement, you have to put your data point at some density value. And okay, is this density referred to the maximum density you achieved in the collision, or this is the time averaged for the physics you're interested in, the density you put? Let's say, people talk about 4 times saturation density. What do you mean by this, and how do you estimate the uncertainty on this number? It's a general question. I always wonder.
The answer is always model dependent. For instance, very the point for the P-right data. Okay, you put the P-right result at the normal density. Actually, like by the emphasize in the book, the P-rights really measures the neutron spin around 2/3 normal density, right? And then when you go from 2/3 to normal density, that part is model dependent. So you see vertical bar in normal density, that's going to work directly by experiment. So actually none of the points on the curve on low data, they are all inferred from some model.
Yeah, but there is a little bit better to me at least, like you study the property of the stable nucleus, okay? I mean, this guy is not really, there's no dynamics for this changing.
Right.
In heavy ion collision, you produce a matter, you compress the matter, the matter expand. And what is the saturation, what's the density you're quoting for this, for the
I
matter?
mean, that's a good question. For instance, the pi minus and pi plus ratio is really very hard to pin down a specific density. Okay, you can say, well, around say at this end, around 1.5 times normal density, but there is no.
But is some kind of weighted average?
So do you have the?
There is ways. You can look at the most probable say density where most of the times pi minus pi plus is well.
Yes.
Yeah, I can pull up, I can probably pull up the talk that I took in INT where I discussed this point.
Bill, actually wants to say something.
Daniel,
we didn't do this for symmetry energy, but with DEMA, we had this Bayesian analysis study when we varied the equation of state in different density ranges independently. So by comparisons to data, you can fix your equation of state in different density ranges. Yeah. I mean, they are correlated, of course, but then you have an error bar on that.
But these density refer to some kind of maximum compression or some kind of average.
No. We just said, well, the interaction between 2 and 3 saturation density, between 3 and 4 is this, between 4 and 5 is this,
Sure.
and then you just run your simulation through whatever density it reaches, right, at given energy. So I think you could presumably do the same for symmetry energy as well.
So for example, for the 1.500, the way that we determine the density is 1.5, we use the crossover. So we use I think I didn't do it. I mean, the theorist, Dan Holtzman, take his code DCQMD, and then he just plot it for different chain variant, and they cross over just like the
best fit.
yeah. Then no, it's not just the best fit. They cross over at that particular point, and so then we say that's 1.4. And then there was another paper where they look at more like the average density over the range of the equation, over the range of the interaction for the transport model. From the transport model, it goes to different density. That's exactly. So the average density for that is also 1.4. So that's why there's a little error pattern. But that's a very good point, is that how do you determine the density? We decided that's.
I think we're in discussion.
Yeah, Zito's been waiting for a while, so let's let Zito
Yeah,
ask
sure.
the question.
Okay, this is what I was looking for. Yes.
Yeah, thank you so much for these interesting discussions. I have my own questions, but first I also have some thoughts on the previous discussions. So what I'm thinking is that given one observations and its uncertainties, then what we will have are just the uncertainties of the model parameters. And then by having the model parameters, we will be able to generate a band of this kind of the symmetry energy as a function of the density. So my own opinion is that it's very difficult for us to say that this observation, one certain kind of observation, for example, the measurement of the neutron spin is sensitive to a specific symmetry energy at a specific density, because probably one measurement of the neutron spin will give us a constraint on maybe the symmetry energy in a certain range, not just on a specific point. So so that's what I'm thinking. And actually my own question relating to this talk is that it's a very naive question. So could we go back to the very first page or the second page that you are showing somehow like the merging of two nuclei?
Can I just show the one point that gets to that this is the nature of a crossover ambiguity shown here. If you look at the figure, and many of them have this behavior, that if you look at symmetry energy functions, that you find that the symmetry energy functionals cross at a point. And then of course you could, as you say, you can go and ask with a correlation analysis, you can also assign an uncertainty for the band over here and a certainty for the band over there. And I think that's better. The problem is that if you do that, you have to ignore all symmetry energy constraints that are published, because people don't publish Bayesian bands. They don't publish Pearson correlation bands, but they do publish enough information that you can find out what their uncertainty value is for this point and the error bar, and the value in the error bar. And for people who actually make it possible to get their functions, because you have to analyze their functions to find it. But you can do it. Of course, if I show you, I think I'll let you. This is the one thing I wanted to show. I'll take your next question, but I want to show another figure that shows basically a comparison between a Pearson correlation analysis of isobaric analog states, masses, and neutron skins to the one we have, completely independent analysis. And then you can ask whether it's just noise. I think the things are really remarkably similar.
Why don't you show it?
Okay, yeah. Oh. Oh, yes, darn it. I think I'll have to stop now because I don't have it right. Oh, here it is. So this is I had a better plot of this, but this is basic. This is, the red line is our contour. These dash points here, which are either side of the red line, are the 1 sigma boundaries for Powell's Pearson correlation analysis of isobaric analog states, and neutron and asymmetry skins. So I mean, that was only one. We took only 1 point here, basically, not using the full contour. We used only 1 point there. From that, we could remove that. It wouldn't make any difference to the curve. They're basically the same. So I think, you know, your point about the need to do a Bayesian analysis or Pearson correlation analysis of function densities, without doubt, correct. But that doesn't make the analysis we present wrong.
But actually, that's what we did in the equation of state determination. We did Bayesian analysis of all these points plus other points.
Perhaps Z wanted to see that science, I think the collision on slide number 2.
Slide number 2.
Yeah, I think it was just like.
Slide.
I cannot remember exactly. It's just those are very interesting pictures showing the merging of 2 nuclei, not the merging of two neutron stars.
This one? Okay, yeah.
I think it's from the science.
This one here.
Yeah, this one, right. So, yeah. So yeah, this picture looks very beautiful and interesting to me. So my question is very naive. So I'm just wondering, so how well can we describe the nucleon density distribution, for example, in the middle, in that middle picture, where all those 2 nuclei are already somehow merging with each other? And
talking about the left. You talking about the left figure or the right figure?
I'm talking about the left-handed side figure for me. Yeah.
These are contours. I think purple was a contours of constant density that I got from Pavel Danielovich for a specific BUU code. It is only showed there as an illustration. And I asked him to give me a slice on the pressure through the center region between the 2 nuclei, and a slice horizontally on the density. So it's just the result of a calculation. So it's a calculation. It's not data.
So is that
On the right hand side? The right hand side is what you get like it's. Huh?
It is a contour of what? Are those the contour of the density or a contour of the pressure or something?
Well, there are 3 figures. Okay, so there's a 3-dimensional figure. The 3-dimensional figure, I think, is something like 5 or 10% nuclear density. Smooth, of course, but it's pretty smooth already. And the arrows are just values for a scale value for the flow in the plane perpendicular to the beam here at the center point. These are gold and gold nuclei, and that's just a scale value, mean value for the elliptical flow. And then over here in the bottom, these are just average test particle velocities in the BUU calculation. That's snap in time. And what's plotted here, these contours are the density contours in the calculation. So this is just an illustration. It's not.
And the top one is pressure, right?
The top one is pressure and the bottom one is density.
Okay. So it seems that we can write it somehow by using this BEP PBUU model to somehow calculate the density distribution when it is already somehow during the merging of these two nucleus.
Because you can get the location of all nucleons as a function of time, you could make this plot anytime you want. So
okay.
the data, the constraints are obtained by looking at the physical observables, the flow observables, and then over all the range of energies that were measured by the EOS collaboration, both at Berkeley and also at AGS. And then, of course, there is a difference. People who are experts know that there's a difference in the preferred values for the equation of state for the elliptical flow and the transverse flow, and those were taken as bracketing numbers for the equation of state. Yeah.
Okay, all right, let's stop there and thank Bill very much for